for coming to this virtual. Okay. Thanks everyone for coming and to this virtual talk. Our speaker today is Jennifer Garden from the University of Edinburgh in Scotland. Jenny is graduated from Strathclyde in Glasgow, where she did her PhD with Rob Mulvey. Then she went to London to do a postdoc for 2 years with Professor Charlotte Williams, where she developed some catalysts for polycarbonate from carbon dioxide. Then she got some fellowship, a Ramsey fellowship, and now she's a Christina Miller fellow at the University of Edinburgh. She does amazing work developing catalysts for polymerization. And today she will tell us more about main group catalyst for the selective synthesis of Homo and multi-block polyester. Jenny, the floor is yours.
Okay. Well, thank you very much for the introduction, Charles. Although that's quite a lot to live up to, some amazing catalysis. I'm like, oh gosh, well, we're under pressure now. But I'll try my best. I just want to say thank you to you for the introduction, and also to Etienne for organising this seminar series. I think it's been such a great initiative to have something like this during the lockdown, and certainly my group and I have been watching them most days or as much as we can. And really enjoying having something to look forward to break up a day of writing while we're out of the laboratory. So thank you for that. Okay, so my talk today is mostly going to focus on polyesters. So as Charles mentioned, our group focuses on a lot of catalyst design, and polyesters, well, this is a class of material that, although it's been around for a really long time, with all the current media focus, it's really a class of materials that is receiving an almost renewed attention in some ways, because with the structure of these polyesters, then we have these polarized carbon-oxygen bonds, which create sort of degradation points along a polymer chain. And so one of the materials that's been really highly looked at for this is polylactic acid. Now, I'm sure that this cycle will not be new to many of you, so I don't want to dwell on this in a lot of detail. But of course, if we start from plant materials, such things that have a high sugar content, such as sweet corn or sugar beet, then we can extract carbohydrates, ferment these into lactic acid. Because we have our alcohol and our acid, then we can form oligomers and then transisterify these with heat into a lactide monomer. And what I really want to focus on in the talk today is this ring opening polymerization step to convert lactide into polylactic acid. So there are a number of different types of catalyst systems for this, including organocatalysts and beautiful work in this field, enzyme catalysts, but organometallic catalysts are going to be the focus of my talk today, because these are really still amongst the most highly active and also very selective systems for this polymerization. Now, many of these organometallic catalysts have this kind of general formula where we have a ligand that's coordinating to a metal center, and then we have an alkoxide group. So the Lewis acidity of the metal is something that's really key, and that's something that I'll keep coming back to throughout the presentation today. So with this Lewis acidic metal, then this is an electron acceptor, and so we can coordinate a lactide monomer towards this metal center. That interaction helps to create a site positive charge at that carbonyl center here, which then facilitates nucleophilic attack from an alkoxide group. And this alkoxide group can either be the glowing polymer chain, or it can be the catalyst initiator. We, for a moment, break our carbonyl bond and form a metal oxygen bond, and then as we reform the carbonyl, we can pop open that lactide ring to insert that into the glowing polymer chain. But what I want to focus on today is, I'll just quickly mention that we can also, this mechanism that I've shown here, this is a coordination insertion mechanism, which is widely proposed as a mechanism for organometallic catalysts and for this ring opening polymerization. But similar mechanisms have been proposed for caprolactone and beta-butyrolactone. But what I want to focus on today is the nature of this metal alkoxide species, because this is a system which is often formed in situ. Sometimes we don't know exactly what the nature of that species is, and the solution state structure can actually have quite an influence on the reactivity of the overall initiator. And so today there are two stories that I'm hoping to speak to you about. The first one, hopefully everyone can see this. I'm going to move you all down to the bottom of my screen. Hopefully you can see the right-hand side of the screen here. But the first story that I'd like to tell you is some work that we've done in our research laboratory, where we've looked at taking a metal carbon bond, reacting this with an alcohol to form our metal alkoxide in situ. But we've seen that there's really quite a difference in terms of activity between whether we have the in situ catalyst or the isolated metal alkoxide species. And then in the second half of the talk, I'd like to talk about using metal chloride groups to initiate ring opening polymerization, and how, while many of these don't show high activities towards lactide, we can start to convert these through using an easier target. So a really highly strained three-membered epoxide ring to generate a metal alkoxide group in situ. Okay, so to start with the zinc system. So this work is work that's been done by Veronica Grushka, who's a terrific PhD student in the group and has worked really hard. So a lot of the results that you'll see over the next 15 minutes or so will be things that have come out of the first year of her PhD. So we saw this system in a talk by Barry Trust, and we were really intrigued by this because polylactic acid is a material that is biocompatible. It can be degraded into lactic acid. So there's lots of applications in biomedicine for this material. But as tin is one of the most commonly used catalysts, there's a real interest in looking at biocompatible metal systems to catalyze these transformations. And at the moment, zinc are some of the most active systems for this. So if we look at the catalyst structures that I've shown on the right-hand side of the screen here, you can see there's this example from the Coates group, and this example from Hillmeyer and Tolman. And these two species are both dimeric zinc species and display really, really high activities for the ring zinc polymerization. But the system on the right-hand side is a little bit different because here we just have one ligand system that's holding two metals within it. And I realize I'm going to be about the size of a postage stamp on everybody's screen just now, but hopefully if you can see what I'm doing. This system was really intriguing because it can adopt a folded conformation where the two metals are held in close proximity, and that species has really high catalytic activity. Or alternatively, that can flatten out, and that brings the two metals further apart from each other. And in those cases, the reactivity tends to drop off. And so this was something that was really intriguing because this made us think, okay, well, the metal-metal proximity could be quite important. And with this system here, we have a ligand system that's designed to have two metals close to each other. So we thought we would have a look at this in the context of ring opening polymerization. It's also quite straightforward to synthesize, and the ligand itself is commercially available, and we can deprotonate that just with two equivalents of diethyl zinc to access this complex in high yields. And this complex on its own is inactive towards ring opening polymerizations of cyclic esters, at least the ones that we've tried, and under our conditions, we haven't seen any reactivity. But when we add one equivalent of an alcohol, such as benzyl alcohol, to this to generate the zinc benzoxide species, then we do start to see activities towards ring opening polymerization. So when we started off testing this complex, we were honestly a little bit disappointed by the activities. So if you look here, you can see that after 1 hour, we only had 21% conversion. So unlike some of the other zinc catalysts that we've seen, this was really not matching up in terms of the activity. But then we tried to switch this to toluene solvent and saw a really dramatic reactivity enhancement. So you can see that now, instead of having 20% after 1 hour, we now have conversions than that in just 20 seconds. So we were really curious to know why. Why were we seeing this reactivity increase? So toluene and THF are clearly having a difference. Initially, we thought that this might be due to the aggregation state because THF is known to be a loose donor because that's decreased the aggregation state. But we looked at DOSY NMR spectroscopy of this complex, both in toluene and in THF. So this is the spectra for THF that's shown on the screen here. So for anyone who's not familiar with DOSY NMR, this is a method of looking at the size of a species in solution. And so we can see this diffusion coefficient, and this links to how big or small a molecule is. If something is heavy, then it tends to come higher up, and if something's small, it comes and lighter, it comes further down that spectrum. And so this showed us that while this complex was monomeric in both THS and toluene, so no difference that we could see in terms of the aggregation state, there was one key difference between the two spectra. So here you can maybe see that the THF is partially in the same diffusion coefficient as the ligand. And this suggests that we have an equilibrium where THF can be coordinating to the complex and can also be free, which makes sense because it's an excess. So if we look at zinc here in the catalyst system, then zinc is a metal that we know likes to be 4-coordinate. And ethyl is a really poor bridging group. And so we have a spare coordination site here for zinc, which would rapidly coordinate THF. And so what we think happens is that in THF, we can block the monomer access towards the zinc. So we're preventing that activation towards that nucleophilic attack and ring opening. So in order to look at this in a little bit more detail, we tried adding 2 equivalents of THF into the system. And you can see that this decreased the conversion from 87% to 80%. So this might not look like a massive difference, but this is in the late stages of the reaction where we're kind of in that plateau region. And when we add in further equivalents of THF, we decrease that all the way down to 58%, so really quite a significant drop-off in activity. So just have a look at some of the polymerization numbers in a little bit more detail here. So you can see that our observed molecular weights were slightly lower than the calculated molecular weights, although our dispersities were relatively narrow. And the reason for this slight mismatch between the observed and the calculated molecular weights became apparent when we looked at the MALDI analysis of the end group. So you can see that we have benzoxide end groups as was the key and the expected end group for the polymer, but we also saw these ligand systems present. And if we come back to look at the structure of the active species, then this maybe isn't massively surprising, because here we have another group which is essentially a benzoxy group. The reason, or one thing for me to highlight here, is that we don't think we get any initiation from this group, because when this is an ethyl, we don't see any reactivity. And we think the reason for that is because we have this enhanced chelation stability in the starting complex. But once we have kicked off that polymerization and we do that propagation, then we can start to have transesterification occurring from the ligand group here. Just to highlight, we had hoped that because this is a chiral ligand system that we might be able to achieve some control over the tacticity, but our symbiotic analysis shows that this is an atactic polymer. But we were really surprised when we looked at using this catalyst as an isolated species rather than generating it through the alcoholysis in situ. We saw a really dramatic reactivity enhancement. So this is the isolated species, which is 10 times faster than the in situ generated species. So you might be thinking, okay, well, this is just because when we added the alcohol, not all of the reaction occurred. And so it might just be that not all of the catalyst was activated. But there are 2 reasons that we don't think that that's the only answer. The first is that when we do the reaction between our zinc ethyl precursor and the benzyl alcohol, the reaction is complete by the time the NMR tube reaches the instrument. And that's at room temperature, where these polymerizations are done at 60 degrees. And the other reason is connected to the molecular weight. So if we look at the GPC analysis, this is for our isolated zinc alkoxide species. And here we see that the observed molecular weights are slightly higher than the calculated molecular weights. If anything, this suggests that here not all of the catalyst species is active. Whereas those of you who are paying attention might remember that in a few slides ago, that we saw that the molecular weights observed were actually lower than what we would expect. So it seems that there's something else going on here. And in terms of the DOSI analysis, so this reveals that when we start with our isolated species, we see a predicted mass, and we obtain this from comparing our diffusion coefficients to a calibration plot. And so our predicted mass is actually close to double that of this monomeric species. So this suggests to us that we have an aggregated species or a dimeric species in solution. And this contrasts with what we saw for the zinc ethyl precursor, which was monomeric. So what we think is giving one of the main reasons for this difference in activity is a difference in aggregation states between either starting from the isolated alkoxide or generating that in situ through an alcoholysis reaction. So just to benchmark this against some of these front-running systems here. So in comparison to the dimeric systems, then you can see that our catalyst is behaving quite well. So these are admittedly all under different conditions, but you can see that ours is sort of 2 orders of magnitude or 1 order of magnitude faster than the dimeric systems. We still don't come close to the really, really fast system by Williams and actually by Charles as well. But we were really quite pleased with this activity. And one of the other advantages of this complex is its versatility. So we looked at expanding the scope of the system to look at caprolactone and beta-butyrolactone. And in terms of caprolactone, you can see that we still have good activities. We have reasonable control over polymerization. Interestingly, there's not such a significant difference here between the isolated and the in situ generated species. When we have a look at beta-butyrolactone, then we again see good activities both in neat beta-butyrolactone or doing this polymerization in toluene solvents. And I just want to focus on some of these beta-butyrolactone results in a little bit more detail because there's not many zinc catalysts known for this transformation. And you can see that we have relatively good control over the system, so our dispersities are fairly narrow. But what was really interesting was the symbiotic bias. So as far as we can find, this is the first zinc system that gives a symbiotic bias for this polymerization. Enzyme catalysts are known to give essentially perfect control over these systems. And there have been some really beautiful catalysts developed, including this yttrium system by Carpentier, which have achieved really, really high symbiotic biases. Being able to access this sort of intermediate range is something that seems to be quite interesting. But because we've managed to use this catalyst for different monomers, we started to think, okay, could we use this to build up copolymers? And I suppose our key learning from this is that the order of the monomer addition is really important for this. So we started off by having a look at the polymerization of lactide first, and then adding in caprolactone. And so you can see that while we have some conversion of the polylactic or the lactide into polylactic acid, and when we did the caprolactone polymerization for 10 minutes, we essentially saw no polymerization. And there are some suggestions in literature that growing polylactic acid chains cannot initiate caprolactone, but it seems that we can do this here because when we extend the reaction time for caprolactone to 6 hours, we do start to see some conversion. And this is increased much more significantly by extending that reaction period to 24 hours. But you'll notice here that we have these signals marked B and D down here. Hopefully you can see that on the screen. And these signals come from linkages between a lactide unit and a caprolactone unit. So B being from the caprolactone, D being from the lactide. And so what this showed us was that because we can see significant signals for D and B, that we really have a random or a weakly gradient copolymer. But when we switch the order of addition and we start with caprolactone and then add lactide, then we seem to be able to generate block copolymers. So we've assigned the structure of these on the basis of a few different pieces of evidence. One of them is the proton NMR spectrum. And so you can see that we have really clear signals for our polylactic acid and our polycaprolactone signals. And we don't have significant signals for the linkage unit. We can see really trace signals when we dig down into the baseline, but they're certainly not as significant as they were with the reversed order of addition. In terms of our size exclusion chromatography, we can see that we increased the molecular weight from the polycaprolactone to the polycaprolactone block polylactic acid unit. In terms of our DOSI analysis, then we see the same diffusion coefficient for the polycaprolactone and the polylactic acid signals. So again, suggesting that we have one chain. And then, or we have a block copolymer structure, I should say. And then we've also had a look at the DSC analysis, and we see the TG of 55, which corresponds to lactide, and another one around -60, which corresponds to the polycaprolactone block. So this was quite nice because whereas before we needed to extend the caprolactone reaction time to about 24 hours, in this case we can actually synthesize these copolymers by reacting the polycaprolactone first, or caprolactone first for 5 minutes, and then within just 2 minutes we can do the polymerization of the lactide. And so as far as we're aware, they seem to be the fastest catalysts reported so far for this block copolymer synthesis. From what we've seen in the literature, most others seem to take between 1 and 96 hours, so we're quite excited about how fast these seem to be performing. So we then sort of thought, okay, well, can we try expanding this out to other other monomer combinations? And so we've taken lactide and beta-butyrolactone, and through using these two, then we can form the polyhydroxybutyrate polylactic acid copolymers. And one thing that seems really interesting here is that it doesn't seem to matter what our order of addition is. In both cases, we seem to end up with block copolymers. Alternatively, taking caprolactone and beta-butyrolactone, we haven't been able to selectively synthesize the block copolymers. The analysis suggests that we just have Homo polymers of these two different species. We think there's a chance that that could be correlated to the fact that there's a more similar activity between these two systems here. But what was really nice is that by combining all three and taking what we found out about the importance of the order of monomer addition, we were able to synthesize these terpolymers. So starting with the polycaprolactone block, and then the lactic acid block, and then the beta-butyrolactone block, then we can synthesize these terpolymers. And this was quite exciting because from what we found in literature, we think this is the first example of this terpolymer being synthesized in a one-pot reaction. I won't go into all of the characterization in a lot of detail, but we have used SEC analysis to do this. And so you can see the incremental increase in the molecular weight as we add the different monomers. And you'll also notice that dispersion. And this is the NMR spectrum here. So we can again see signals from the block copolymer structure, again with only trace signals for the linkage units between those different blocks. So this is something that is still fairly new from our laboratory, and we're very keen if anybody is looking for any materials like this or has any thoughts on potential applications, then I'd be really happy to discuss this either in the questions at the end or feel free to follow up with me afterwards. So in the second part of the talk, then I'd like to focus on using these metal chloride species to initiate ring opening polymerizations. So for this part of the talk, I'll focus on this saline ligand scaffold, which I'm sure many of you will have seen before. So this Jacobson catalyst is something that's been ubiquitous through a range of different catalytic transformations, and it's been particularly successful within ring opening polymerization. So the conventional way to do the initiation is similar to what we saw with the zinc systems in the last part of the talk, where we have a metal carbon bond that's converted to a metal alkoxide bond through a reaction with an alcohol, and then that can initiate the ring opening polymerization. But there was a really nice paper a few years ago from Thomas Amaron and co-workers, where they looked at initiating through an aluminium chloride bond. Now, usually aluminium chloride bonds are really strong and they're not always that active in terms of initiating polymerizations. But what this group did was they took an epoxide as well as an ammonium salt and used this as a method of converting it to the aluminium alkoxide. And then from here, they could use this to initiate the ring opening polymerization. So the ammonium salts, so ammonium or phosphoammonium salts, were proposed to enhance the initiation through acting as a Lewis base and coordinating to the metal center. So what I mean by that is if we take this salt, so something like PPNCl with a chloride anion, and that chloride can act as a Lewis base and coordinate to the aluminium. Now, because we have aluminium, which is a 3+ metal, and we have initially 3 anions, now 4 anions around it, there's overall a negative charge, and so this is called an 8 complex. And this 8 formulation is thought to increase the nucleophilicity of that chloride group here. So that can then react with an epoxide and ring open that to form this aluminium alkoxide chloride species, which can then react with another epoxide to form this 8 type species of this alkoxide. And in this mechanism, this is what the group proposed was the active complex for this polymerization. There's another way to get to this species, which would be through directly ring opening an epoxide to form the aluminium alkoxide. And then because we can get transfer of these alkoxide or these chloride anions, then you could have transfer from a ppNOR unit to form that same species. So while this was a really landmark paper, there were still a few limitations associated with the system. And one of them was that it needed this propylene oxide, this epoxide, as the solvent. And this is a material that's really quite toxic and also has very low boiling points. It's around 35, 36 degrees for the boiling point, which can limit some of the temperature range that you can use with the crop. And it also required expensive ammonium salt co-catalysts such as PPNCl, and there needed to be an overnight pre-activation of catalyst components. So if I just quickly go back to the last slide, this PPNCl, the aluminium chloride species, and the epoxide had to be stirred together to generate the active species before the lactide was added. And then there was still a 4-hour initiation time. So we were really keen to see if we could start to modify some of these features. And could we access toluene because it's a higher boiling point solvent and it's also a little bit less dangerous? Could we avoid the use of this external Lewis base by incorporating an electron donor into the ligand scaffold? And so could that also help to avoid this overnight stir that we needed for activating the catalytic components? And so we were keen to look at introducing electron donating groups into that ligand backbone so that we could push all that electron density up to the aluminium center, and then that should lengthen and weaken that aluminium chloride bond. So would that mean that the aluminium chloride could ring open that epoxide without that external salt? So that was what we were hoping to do. So in order to test this, Jay, who's a terrific PhD student in the group, looked at making a series of different complexes. So this is a simple shift-based chemistry reaction. It's a diamine and 2 equivalent aldehydes to form a ligand. From here, it's a simple dideprotonation using dialuminium chloride to generate this species here. And you'll note that we have these strong electron donating groups, these dialuminium groups on the meta positions here. One of the reasons for this is if you look at this lone pair of electrons and imagine them on that nitrogen there, we can see localize all the way through that ring and put that negative charge onto the nitrogen, so directly next to the aluminium. So that was one of the reasons for us looking at these systems. So our question here was really, do strong electron donating substituents increase the nucleophilicity of this aluminium chloride bond? And does that help us to ring open the epoxide to form the active species? So we were able to crystallize one of these complexes and to look at this by X-ray diffraction. And this was really interesting for us because while we can see that the aluminium is 5 coordinates, so fairly standard, and the aluminium nitrogen and the aluminium oxygen bonds are fairly standard, fairly typical in their length. And this gave us insight into the aluminium chloride bond. And what we see is that this bond is significantly longer than other aluminium chloride bonds from saline complexes in the literature. And because this is much longer, this also suggests that it's weaker. And so this suggests that it's better able to react to the labile nucleophile. And so we were quite pleased when we saw this. So moving on to testing these systems in terms of their catalytic activities, you'll see that there are 2 complexes here that really stand out in terms of their activities. So these are the 2 systems where we have this 3-carbon linker in the backbone, the diamine backbone here. And so they're really significantly faster than these 2 systems, which is where we have either just a 2-carbon linker or a 2-carbon linker as part of the cyclohexane unit. So this is something that fits with this work shown down at the bottom by Gibson and co-workers, because having these 3 carbon linkers gives increased flexibility around that catalyst system. That sort of enables the molecule to contort and twist into different conformations to access transition states more easily. But we were quite pleased at the activity of these 2 species. And when we compare this to the Jacobson system, the system that was originally initiated, and you can see that we've not just decreased the initiation period, but we've actually significantly increased the propagation rate as well. Now, these reaction conditions were done in toluene solvents. We can access higher temperatures here. So we were curious to understand what was going on in terms of this initiation in a little bit more detail. Because although the kinetic plots in the previous slide suggested that our complexes were faster initiating, there's always a little bit of error associated with the kinetic plots. So to try and get a little bit more of an understanding for this, we had a look at this through NMR spectroscopy. And we can see that with this aluminium chloride system, there's also a possibility for this to either attack the epoxide at the CH2 position or the CH position. So firstly, we had a look at the time it took for this reaction to go to completion. And we can measure this by the increase in terms of the ring opened epoxide signal shown here around 4.5. And from analysing this, you can see that it's about an hour for us to get to complete conversion of that reaction. And this is significantly faster than what we saw with the Jacobson system, where it takes around 4 hours for that reaction to go to completion. I'll mention that these reactions were done in toluene to mimic the polymerization solvent, but these are reactions that are done at room temperature, whereas the polymerizations were carried out at 120 degrees Celsius. So the initiation in terms of the polymerization is much more rapid than what we're seeing in the NMR tube. So in terms of the second question we had, and which site of the epoxide was attacked, there's sort of literature precedent for both of these to occur, but what we see is that it's the less sterically hindered CH2 position that's attacked and ring opened in our structure here. And we were able to assign that from the protein NMR and the HPCM analysis. Okay, so we then started to think about this because we were like, okay, we were able to get faster initiation, which is really positive. But there's always this trade-off. If we're introducing extra electron density into that catalyst system to increase the initiation, then we're also likely to have a trade-off in terms of the propagation rate, because we know that one of the key steps is thought to be this monomer coordination and activation towards attack. So if our metal is not really acidic enough, then we're going to be disfavoring that coordination. So we started to think, okay, are there going to be better substituents that we can try? What about if we take something that's not as strong an electron donating group? Can we then still have that increased efficiency for the initiation, but can we actually then start to improve the propagation as well? And so, as well as the original diamine substituents that we looked at, we also looked at ether substituent, a slightly weaker electron donating group. This is work that was carried out by Annie. This is a photo of her when we were allowed llamas to come to the university to make sure that nobody was getting too stressed out. Yeah, this is work from her master's project. So not to keep you in suspense any longer, but to show you the difference in activities, and this is for the 2 carbon linker here. So you can see that we have a significantly faster activity when we have our methoxy group, so the darker blue line here, in comparison to the pale blue line here, which is our original amine system. So this does seem to suggest that by having this weaker electron donating group, we are able to increase monomer coordination towards the aluminium site and enhance the reactivity. The effect is not quite so pronounced when we move to our 3 carbon system, but the trends are still the same. So you can see in the yellow here compared to the orange, this is our 3 carbon linker, and then the grey is our methoxy versus black, and the difference, these are our 3 carbon linkers with 2 methyl groups on the central position as shown here. So So we then wanted to have a look at what was the influence of the regiochemistry of that methoxy substituent. So we knew that it increases propagation rate, but what about the influence of where that substituent sat, and was that important? So Annie had a look at preparing the ortho methoxy, the meta, the para, and the meta dash positions here. So we plotted kinetics for all of these complexes, but the one that really sticks out here is the ortho-substituted complex. As you can see that the rate with this complex is almost double that of each of the others, and actually the other three are fairly similar in terms of their propagation rate. Notably, in terms of the initiation, then we have quite a similarity between the ortho and the para system. So this maybe suggests that the electronics are important, because if we think about the ortho and the para and sort of drawing out those resonance structures, then we can have the same resonance isomers when we do delocalization. So this is maybe an indication that the electronics are important with regards to the initiation. But we also wanted to have a look at the initiation in more detail, and again having a look at the SPI and the MAR studies. So this work was done by Zoe Grindle, who's just finishing her bachelor's project in the group at the moment. So when she looked at these by NMR, then there are two features that were really similar. So the ortho was significantly faster than the rest of the species, and the meta was really the slowest. So this mimics what we see at the top here. But there is a switch in order between the meta dash and the para systems here. So if we sort of look at these NMR and the kinetic studies together, then this sort of points us towards the fact that there's an electronic influence, and so the ortho and the para generally giving faster initiation in the meta dash and para systems. But it also suggests that there's a proximity influence, because when we have this ortho substituent here, we see a much faster initiation in terms of the NMR studies than the para. And similarly, with the meta dash, so being directly adjacent to that imine group, and indeed we can delocalize the electron density onto that group here, we see a much bigger effect with the meta dash substituent compared to the meta substituent. But one thing that was quite intriguing about this was that the orthomethoxy gave us the highest tacticity control. And this on its own is not particularly surprising. With catalysts of this structure, then it's been shown that when you have a bulky butyl substituent in the ortho position, that this increases the tacticity control. And this makes sense because you have this steric bulk close to the metal center. This really forces one particular orientation of the monomer to line up and to coordinate to that metal center. But the interesting thing is that increase in tacticity control usually comes with a drop-off in reactivity, because you have that extra time for that monomer to line and to coordinate. And so usually the higher the tacticity control with this type of scaling system, then the lower the activity. But here with this ortho complex, we have something that seems a little bit too good to be true, because it's fast, it's in terms of the initiation and the propagation, and yet it still gives us that tacticity control. So we were thinking about why this might be happening. And what we think is that we kind of have an electronic tug of war happening, where we have this lone pair of electrons on the oxygen, which is in the p orbital, so that can be delocalized throughout that pi cloud, throughout that aromatic system. And that can then coordinate electron density towards the aluminium, increasing the mobility of that chloride group and giving efficient initiation. But while we have this electron donating group, and indeed methoxy groups are typically thought of as electron donating groups, we also have a really electronegative oxygen. And so if we think about this in terms of the sigma effect, then this can withdraw electron density. And so we think this is enhancing the acidity of that metal center. And then because we have this increased steric bulk at the ortho position, then we think this is why we're able to get some of that tacticity control. So it seems to be the best combination, and most pronounced when we have this directly adjacent to that phenoxide oxygen. Okay, so just to conclude, so here we have looked at different ways of generating these metal alkoxide species, starting off with the zinc carbon group and converting that into zinc alkoxide through reaction with an alcohol. And we've seen that this isn't always as straightforward as it might appear. So even if we get good activity in terms of the alcoholysis, then actually things like the aggregation state and what's happening in solution seem to play a really important role and provide an easy method of increasing the catalytic activity by a factor of 10. We've also shown that we can have this complex being active for a range of different monomers, including lactide, caprolactone, beta-butyrolactone, and indeed we can use this to build up block copolymers through sequential addition of these different monomer units to achieve the first pair of polymers with these three cyclic esters, and also achieving some syntactic control with the beta-butyrolactone system. In terms of the metal chloride system, then we've been able to, through modification of the ligand scaffold, to develop systems that can efficiently initiate even with as low as one equivalent of the epoxide. And by incorporating electron-donating groups into that ligand scaffold, we've been able to circumvent the need for an external fluid base, such as TCNCl. So in my final slide, I would just like to say a huge thank you to my group for all of their hard work, all of their enthusiasm, and all of their determination. The chemistry is really thanks to them, and to them for having faith in me and being part of my very new research group. So I'm really grateful to them and all that they've done. And so I've tried to highlight people as we've gone through, but this is all of us standing with David Brewster outside the front of the University of Edinburgh. I'd also like to thank Michael Schaefer, who's been a terrific mentor and support to me from when I took up my fellowship at the University of Edinburgh, and for funding the Ramsay Memorial Fellowship, which I currently hold, and the Criticat CDT, who funds Veronica's PhD student, and the Royal Society and the Women in Science Fellowship as well. And finally, thank you very much for your time and for listening.
There's already one question. Do you see it on the chat?
Yeah, I'm just opening up this just now. Okay, so shall I start by reading out the question?
Yeah, you can.
So if anyone can't see it. Okay. So thank you for the question. So the question is, have you carried out any comparison studies between your organometallic species and model metal-free organocatalysts in terms of bringing polymerization kinetics, molecular weight, and activity control in your systems? So the short answer is no, we haven't yet. We have started to look at some computational studies, but these have mostly been connected to some of the mixed metal systems that we're working on. So what I presented on today are kind of our first tier of the catalysts that we're developing, and we're currently at slightly earlier stages of some mixed metal systems. So we've been doing some work in terms of having a look at what metal goes where and why some of this can give some of these enhancements that we see. But in terms of this, I'm afraid I haven't really got any data on that at the moment. If there's anything you think would be particularly interesting for us to look at, then feel free to let me know.
Okay, thank you. So there is another question on the YouTube chat. I will read it. So what's the one-pot tri-block caprolactone lactic acid PHB copolymer made by sequential addition of the monomer, or were they all added at the beginning and present through the whole reaction?
Sorry, actually, I'm not sure I quite got the last part.
I will copy past the question. It will be maybe easier. And you see?
Thank you. Yeah. Okay. Yeah. So yes, the one pot tri-block copolymer was made through sequential addition. The one where we've tried adding everything at the start and seeing how it unfolded. The only thing that we've really done that in detail for has been the caprolactam and lactide system. When we add the two of them together, then we see the same ratio of linkages and block units in the NMR as to what we do when we add the caprolactam first and then the lactide second. So we think that in that case, it's probably controlled by the reactivity ratios of the different polymers. But it's certainly, certainly quite random. But no, in terms of synthesizing the terpolymer selectively, then we found that we needed to do that through sequential addition. Okay, I'm seeing some more questions in the chat, which is really kind of everybody. Etienne, how would you like to do this? Do you want me to read out the questions? And
you can read. There is two more questions. There is one from Pierre Lalanne, I guess, and one from Thomas Bennett. You can read them if you want to answer them.
Sure.
And I have also some by myself too, but later.
Sure. Okay, perfect. Okay, so Pierre, thank you for your question, which is about the evolution of the polymer dispersity with the conversion. So with the BIS-SYNC systems, then they're fairly consistent, but they do start to increase towards the end of the reaction. With the aluminium systems, then there's a much more significant increase in the dispersities once we get past conversions of about like mid-70%. So yeah, we certainly do see that being much more significant in the aluminium systems. We think that it's because we can get with some of the aluminium systems, depending on where that substituent is, and particularly when it's in the meta para position, then our dispersities become larger towards the end of the reaction. And we think that's because we have the formation of some cyclics. So because we have a bit more space around the metal center, then we think that can help to promote the formation of cyclic polymers once we're in the late stages of the reaction. So yes, that's certainly something that we see in terms of the MALDI analysis. And yes, in the later stages of the reaction with the substituents and those substituents, then it's a little bit more pronounced. We're still under a dispersity of 2, but we get up to dispersities of around 1.6, 1.7 towards sort of 80–90% with the meta substituted aluminium systems. Some of them are a bit lower than that. Okay, so then, hi Tom. So thanks for your question, which is about, do we want to undertake all of the polymerizations with the zinc catalyst in bulk or in greener solvents? And have we done any thermomechanical characterizations, dye block or tar block copolymer characterizations, which might change as a function of composition? And it being interesting to look at them with STM, the self-assembly behavior. Wow, there's a lot of good suggestions in that one question. So at the moment, then the zinc catalyst, we've done everything in toluene because that's the solvent that we found to be successful for the individual Homo polymerizations. And so for doing that sequential addition, then it's something that that works well. I think we did do the lactide polymerization in bulk, and we found that it worked. But I think our results were actually better in toluene. But there would certainly be opportunities to try that with some of the monomers in bulk, especially the fact you need the lactone seems to work well. So it's an interesting question. It's something we haven't really done much of, but we should maybe think about. In terms of greener solvents, that's also a really good point. And I suppose things like methyl substituted THFs and things might be really interesting to investigate, because although THF shuts down that activity, if we have something with a lot of bulk in the positions next to that oxygen, can we then start to stop shutting down that polymerization? So yeah, there's a lot that we could think about in there. In terms of thermomechanical characterization, I mean, we've literally just done the DSC studies on these polymers at the moment, and then the NMR and FTC studies that I showed. And there's certainly a lot more that we could do in terms of optimizing the systems. It might be a good idea for us to have a follow-up chat after this. And then, Etienne, your question about the tolerance of the catalyst to water and air. Yeah, that's a good point, especially with the aluminium systems, because one of our motivations for doing this is the fact that the aluminium chloride bonds are often less reactive than much less reactive than the aluminium carbon bonds. So we have done some preliminary studies, but mostly taking the catalyst and looking at these in solution. So I was studying them by NMR to see if we see any decomposition, rather than testing our polymerizations with walking additives or things like that. With the aluminium chloride systems, then we do see that there is some stability to air. So if we take the catalyst intolerant solvent, we open it up, and then we refill the tube once we shake it with air, then we see that the catalyst is stable over about an hour, maybe 2 hours with some of the systems, but beyond that we start to see some degradation. But certainly with respect to the aluminium carbon systems, then they're much more tolerant. We haven't really done any more detailed studies than that at the moment, but it's something that we've certainly been talking about and would be interesting to do. In terms of the zinc systems, it's not something that we've really tried yet. The zinc alkyl bonds are certainly very reactive. The zinc alkyl oxide groups, we haven't actually looked at that yet, but it's something that we've just think about.
I have also one question by myself. So your first catalyst, it appears extremely versatile, and it's working with a lot of lactone. So did you try large ring lactone, such as pentadecalactone or this kind of?
Oh, we haven't yet, and again, it's something that we would really like to do, and it's just one more of these frustrations about the lab being closed down at the moment. But yeah, no, certainly testing larger ring lactones would be a really good thing to do. I think Veronica's in the audience, so I'm hoping that she's frantically scribbling down some of these suggestions for when we can get back into the lab. I'm seeing another question on the Zoom group chat as well, which is about whether the catalyst can tolerate other solvents other than CHF and toluene. So we've not extensively tested, but we do have 1 or 2 data points in dichloromethane, I think it was. I think it was dichloromethane. It's either that or chloroform, but I'm pretty sure it's dichloromethane. And we see that the catalyst can tolerate that as well. This is with the zinc work, I should say. And with that, then we see that similar to THF, there's a little bit of an activity decrease, which we think is because we have that chloride that can act as a donor. So it's not as marked as what we see with the THF, but we just have like 1 data point which suggests that it is tolerant, but again, it decreases the activity, probably due to coordination and blocking the metal site for coordination of the monomer.
Okay. Is there any more question? If no, maybe we can close the session. So thanks again, Jenny. It was an amazing talk, and I hope you enjoy it as much as I do.
Well, thank you very much. Yeah, it's been an absolute pleasure to speak, and yeah, I'll look forward to seeing you all online at the next one.
Yeah. So, bye. See you. Thank you again.
Thank you very much. Bye.